Okay, so there's a special definition for a chemical bond. Can anyone tell me what a chemical bond is? Any idea? Two things together, right? So chemical bonds, its actual definition, right? Its book definition is a mutual attraction between the nuclei and valence electrons. That's how I abbreviate valence electrons. Okay, an E with a little minus sign. How I write electron. Okay, just save some time. So VAL means valence, E is electron. So the mutual attraction between a nuclei and a valence electrons of different atoms. That bring those two atoms together. Valence electrons are located in the outermost electrons, and valence electrons are the only electrons that are available to bond. Okay, inner shell electrons are full shells. Outer shell electrons mean that they maybe don't have a complete shell. Okay, do you remember how many electrons it takes to be a complete shell? 8, good. It takes 8 electrons to be a complete shell, and so when we talk about valence electrons, the max we could have is 8. The minimum we have is 0 or 1, right? Why would there be an attraction between the nucleus of one atom and a valence electron of another atom? What's contained in the nucleus of an atom?
Protons and neutrons.
Protons and neutrons. And which of those two things puts out a charge?
Protons.
Protons, good. And what charge does a proton put out?
Positive.
A positive. Okay, so in general, right, nucleus, or the nuclei is plural, of atoms gives out a positive charge. Valence electrons, or electrons in general, give out what type of charge? Negative. So positive attracts a negative. Okay? That's why we see an attraction between those two things. So a chemical bond is specific in that there's an attraction and it's strong enough to hold those two atoms together. That's essentially what we're talking about here. Okay, so in general, there's chemical bonds, and we're going to talk about 2 specific types of bonds. Does anyone know what 2 types those might be? Yeah, that's one of them. First of which is called an ionic bond and a covalent bond. Hopefully those things sound familiar to us. Right, we already learned how to name these types of molecules. So now we're going to go back and look at kind of why they bond the way that they do. Okay? So in an ionic bond, what happens is that atoms completely trade their electrons. Okay, they completely trade their electrons. And if you remember, what are ionic bonds or ionic molecules made of? Good, a metal and a nonmetal. Okay, so this happens when a metal and a nonmetal, or if you want to think of it as a cation and an anion, completely trade electrons. Okay, so let's think back to a really common ionic molecule like sodium chloride. Okay, sodium has how many valence electrons? Take a look at, do you remember the pattern for valence electrons? It corresponds with their group number, right? So group 1 has 1 valence electron. Group 2 all has 2 valence electrons. We skip the transition metals. Then over here, group 3 has 3 valence. 4, 5, 6, 7, and 8. Does that ring bells a little bit? Okay. So sodium is in group 1. It has 1 valence electron. So to be happy, right, to have an outer shell, is it easier for sodium to give up its 1 electron or to find 7 more? Give up its 1. Okay, so think about that. Chlorine, on the other hand, is found in group 7 or group 17. So how many valence electrons does it have?
7.
It has 7. Is it easier to give away 7 or to take 1?
Take 1.
To take 1. So in this case, what's happening is sodium is completely giving up its electron to chlorine. And what happens is sodium gives away that electron, which leaves it with 1 less than it should have, which is why it has a positive charge. Chlorine gets 1 extra electron, which gives it a negative charge, and this positive and negative attract each other so much that they hold together. And that's what an ionic bond looks like. Right? We've traded electrons and we've formed these strong charges that now this negatively charged and positively charged atoms will sit close enough together that we consider it a bond. Okay, so that's kind of a little overview of what happens with ionic bonding. Any questions there? Ethan, did you have a question?
What if they both have 4?
So it can go one way or the other. They can give or they can take. It depends on what else they want to bond with. So carbon is one that can go, is the most common one that goes either way. So carbon and silicon can go. So if it wants to bond with sodium, right, it would act as an anion. If it wants to bond with chlorine, it would act as a cation. Good question. Okay. Ionic molecules are not going to be the big focus for this chapter 6. We're going to deal more with covalent molecules, and the thing that happens differently in covalent molecules is that they share electrons. Okay, so in a covalent bond, we see them sharing electrons, not trading. Okay, so when we talk about an ionic bond, that means we've completely given up our electrons or taken electrons, and we hang out close to each other because we have corresponding charges, right, or complementary charges. But in a covalent bond, we see that they completely share electrons, so that you are contributing 2 and I'm contributing 6, so together we have 8 and we're both happy, type of thing. Okay, so covalent molecules, they share. Sometimes they share evenly, and sometimes they share unevenly. Okay, and we'll talk a little bit about what that means. So I handed out this electronegativity scale to you. This is called the Pauling scale, and what it does is it gives each element a value that tells us basically how badly it wants to take electrons from something else. So you'll see on that handout that the most electronegative atom is fluorine, right? And the values increase as we get closer and closer to fluorine. Okay? Why do you think that the noble gases aren't given an electronegativity value?
Because they have 8.
They have 8, right? They don't want to take electrons from anyone. They just are good to hang out by themselves, right? Okay. So the reason I gave you this scale and the reason that we look at electronegativity has to deal with covalent bonds. Okay? And what happens in a covalent bond is they share electrons, but sometimes they don't share them evenly. Okay? So if we contribute electrons to a bond, we might not be sharing them evenly. Okay? So what happens if we share between, let's say, fluorine and calcium? Let's say that those 2 atoms wanted to bond. Which of those atoms wants electrons more? Fluorine, right? It's more electronegative. So if each of those is contributing an electron to that bond, the electrons would be sliding more toward the fluorine side, right? And in this case, it's a metal and a nonmetal, so they might be sliding so far that we would call this an ionic bond. Okay, so there's kind of a sliding scale between ionic and covalent bonds. Let's say we looked at a bond between phosphorus and fluorine. Which of those is more electronegative? Fluorine, right? So if we looked at a bond between phosphorus and fluorine, we could look at the difference in their electronegativity values, and we could decide, are they sharing them evenly or are they sharing them unevenly, type thing. Okay? And when electrons are shared unevenly, there's a certain name for that, and this is called a polar covalent bond. And so what this is when electrons are shared unevenly within a bond. Okay, they're shared unevenly within a bond. So a nonpolar covalent bond, what do we think that would mean?
They're shared evenly.
Good. Okay, and so this is a little bit counterintuitive, right? For polar to be uneven distribution of electrons, and nonpolar means even distribution of electrons. They kind of go backwards, okay? But a polar bond means that something is not being shared evenly, okay? And so there's kind of a scale that we can follow that helps us determine, is a bond nonpolar covalent, is it polar covalent, or is it so unevenly that we would consider an ionic bond? Okay, and so the values for that go like this. To be considered a non-polar covalent bond, the differences in electronegativity values have to be less than 0.3. Okay, less than 0.3. So what this is saying is that if we had a bond between hydrogen and hydrogen, right, what's the difference in electronegativity values between those two? Zero, right? It's the same amount. Each of those hydrogen atoms is pulling on those electrons with equal might. Okay? What about a bond between carbon and sulfur?
0.65 more the carbon.
Look at carbon and sulfur's values again. I think I picked two that were hopefully close together.
0.03.
Okay, so what's carbon's electronegativity value? 2.55, and what's sulfur's? 2.58. So it's not 0.3, it's 0.03. Okay? So these two are essentially, again, pulling on these with equal strength. So each of them wants the electrons just as badly as the other. So we would consider this a non-polar covalent bond because they're sharing them essentially equally. Okay? Does that make sense? What if I looked at now a bond between... let's get the value, for the next one. So to be considered a polar covalent bond, we share them unevenly. The difference in electronegativities could be between 0.31 and 1.7. Okay, so if we have a difference in electronegativity values that falls between 0.31 and 1.7, we would consider that a polar covalent bond. Okay, so an example of that might be fluorine and hydrogen. Okay, so what's fluorine's value?
3.98.
3.98. And what's hydrogen's value? 2 point what? 2.20. Okay. So the value there is what? 1.78. Okay, so we're really, really close there to a polar covalent bond. Might even be sliding into ionic bond territory. Okay, so if it gets over 1.7, we would consider it an ionic bond. They're shared so unevenly that they are trading their electrons. And each textbook has these values. It's a little bit different, but these are general, kind of in that right spot. So if we have a value of greater than 1.7, we would call it ionic. Okay, and you can put that somewhere later in your notes. I don't really have room to put it on this slide. Okay, so greater than 1.7 would be considered an ionic bond. At a bond between hydrogen and sulfur, would we call it nonpolar covalent, polar covalent, or ionic? Okay, you look at those values and decide. So 0.38 means we are in what category? A polar bond. Okay? And between those two atoms, which of them wants the electrons more? Sulfur, right? It's the more electronegative. So if we picture these electrons between these as kind of a tug of war type situation, it would be pulling towards sulfur. Just at the slightest amount. Okay? Okay? So we're going to look at covalent bonds and covalent structures in the form of Lewis structures. Okay, and what Lewis structures are, they're 2D representations of compounds. Okay, sometimes they're called Lewis dot structures, sometimes they're called electron dot structures. I will always refer to them as Lewis structures. Okay? So we've talked about in a covalent bond, or in a covalent, in a covalent bond, how many electrons does each want to be happy? How many electrons do you want in your outer shell to be happy? 8, okay? So the way a covalent bond works is if I am contributing 2 electrons and Gabby is contributing 6 electrons to our bond, right? I get to count her 6, she gets to count my 2, and we each have 8 now. Okay, so we're going to look at how we can draw this and represent this in a two-dimensional structure to show bonds and electrons that complete each atom's octet within a compound. Okay? All right, we're going to just start with drawing Lewis structures of single atoms, which are the easiest kinds, right? We don't do it very often, but we're going to start with single Lewis structure. So if I want to draw the Lewis structure or the dot structure for a single atom, let's start with carbon. Okay, let's start with carbon. How many valence electrons does carbon have? 4, right? So my Lewis dot structure for carbon looks like that. That's it. That's it. Okay? So when we draw our Lewis structures, we're usually going to have 4 sides to our structure. Okay? We want to space our electrons as evenly as possible. So rather than it looking like this, right, we want to space them out as evenly as possible. So we're going to put them around all 4 sides of our atom. Okay? If I went to draw oxygen now, how many valence electrons does oxygen have? 6. So I'll go 1, 2, 3, 4. And then the other 2 that I put doesn't really make a difference, but I want to usually space them out. So I'll go, 5, 6, or I could go on the sides, 5, 6. However you want to do that is not a huge deal. Okay? Questions so far? Unfortunately, we don't draw single atom Lewis structures like ever. Okay, but this is how we're going to get to drawing compounds. Okay? Let's look now at how we can form a bond between two different atoms. Okay? Let's draw the electron dot structure for fluorine. 1, 2, 3, 4, 5, 6, 7, right? And let's say I wanted to bond it to another fluorine atom. Okay? Each of these structures, or each of these atoms, is contributing 7 electrons to this new molecule. Okay, and so if I wanted to bond these 2 things, I'm going to move this guy over a little bit closer. And we see that these 2 electrons here can hang out next to each other, and they're going to form a bond, a chemical bond. And so in a Lewis structure and in any drawing, when we have a bond, we show it with a straight line like that. Okay? So once we form a bond with 2 electrons, that's as many electrons as can be held in a bond, we draw it with a straight line. Okay? So each of them contributed 1 electron. They bound themselves together in a chemical bond, and we draw it with a straight line. Okay? So this right here is a bond. And then all of these pairs of electrons on the outside, they're what we call lone pairs. And any time that we have an electron that has to be represented not in a bond, it has to be in what we call a lone pair. It's got to be in a pair. Okay? And right now, I know this is still a little bit foreign for you. I know maybe what I'm saying doesn't quite make sense just yet, but I think we'll get there. Okay? So each fluorine contributed how many electrons to our structure? Each contributed 7. Okay? So once we've drawn our structure, we've shown that 2 fluorines bonded together, we want to go count our total electrons. So 2, 4, 6, 8, 10, 12, and then how many in this bond? 2 total, so there's 14, right? Now let's look at the purple fluorine. Does it have a complete octet?
Yes.
2, 4, 6, and it gets to count both of those electrons as its own because they are sharing them. Okay, so this fluorine has a complete octet. The red fluorine gets to do the same thing. 2, 4, 6, and 8, so it has a complete octet. Okay? We rarely ever start with single atoms like we just did and put them together. Normally I'm going to give you the compound, and then I'm going to show you how to build the Lewis structure from there. Okay, that was just an introduction to taking single atoms and putting them together. Okay. So the first thing that we need to do if we're given a compound, okay, so let's say we want to start with the compound CCl4, and we want to draw the Lewis structure for CCl4, okay, carbon tetrachloride. That's just an example compound. The first thing we have to do for that is count the total number of valence electrons needed. Okay, so just like we did with our fluorine molecule, we said each fluorine contributes 7. So total in our structure, there had to have been 14 electrons represented there. And we counted them, and we found 14. Okay, we're going to do the same thing for this example. So for carbon tetrachloride, why don't you go ahead and count how many valence electrons we might need to have. Right? Carbon gives us how many? 4. And each chlorine gives us 7. So 7 times 4 for chlorine is 28, plus 4 more is how many? 32, right? So if we use the example CCl4, this structure would need to have 32 electrons represented somewhere in that Lewis structure. Does that make sense? That's the first thing you do is count valence electrons. You can write down a little hint here. This number should always be should always be even, Should always be an even number.
Is there an instance where it ever...
No, we will never deal with uneven number of electrons because they either have to exist in a bond, which is 2 electrons, or they have to exist as a lone pair, which is 2 electrons. So electrons should never come out, valence electron number should never come out as an odd number. Okay? So we're going to count the total valence electrons. Step 2, we're going to arrange our atoms in what we call the skeleton. So what this is all of our atoms without electrons drawn. Okay? And so here's some rules for drawing our skeleton. If we have carbon, it always goes in the center. Okay? So in this example, if we were looking at CCl4, our skeleton would look like this. Right? Carbon goes in the center, and then 4 chlorines go around it. That would be what the skeleton would look like for this example. Carbon goes in the center in all situations. If we have carbon in our molecule, it needs to go in the center.
Is there another one that has the same rule?
Carbon is the only element in particular, and then I'll give you how do you pick it after that. Okay? So if you don't have carbon, if you have no carbon, then the least electronegative atom goes in the center. Okay? And so that's when you would use your Pauling scale, right, that electronegativity table that I gave you, to find the least electronegative atom in your compound. Okay? And I'll give you a hint. It's usually the one there's the fewest of, right? Or it's the one that's listed first in your compound. Okay, so if you're in doubt, it's the one there's the least of, or it's listed first in your compound. Okay? So carbon always goes in the center. If not carbon, it's the least electronegative atom goes in the center. And here's the last little part of this. Hydrogen can never, ever, ever go in the center. Okay, hydrogen can never be a central atom. Can anyone tell me or explain why that might be? It only has one valence electron. So it can't bond to more than one thing, right? It only has one electron to give. So it cannot possibly bond with more than one thing. So hydrogen is never a central atom. You'll get a big like frowny face on your paper if you put hydrogen in the middle. So don't do it. Okay? Hydrogen does not go in the center. After we've counted valence electrons, after we've drawn the skeleton, now we're going to bond the central atom to the outer atoms. Okay, then complete the octets with lone pairs. Okay, so there's good and bad about Lewis structures. The good thing is that there's only 3 steps. The bad thing is that Lewis structures are one of those things that there could be multiple correct answers. And I don't really like that, but that's how it goes, okay? So Lewis structures are can be like puzzles where you have to work a little bit to get them to put them together, but eventually you can get there as long as you check your valence electrons and check your octets. You'll eventually get to that answer, okay? But there could be more than one correct answer, so I'm going to really, really try to keep it as simple as we can for our Lewis structures, okay? Let's try one. Okay, we're going to do some examples here. First one we're going to start is with NH3. Okay, first thing that we do is count our valence electrons. So nitrogen gives how many? 5. And each hydrogen gives how many? So 3 times 1 is 3, which gives us a total of 8 electrons that need to be represented somewhere in our structure. Okay? So we need a total of 8 electrons. Which of those should be our central atom? Nitrogen or hydrogen? Nitrogen. Okay, so as we draw our skeleton, we're going to go nitrogen, and then we're going to space the hydrogens just evenly around. Okay. For right now, since these are two-dimensional, where we place these 3 hydrogens is not a huge deal, but you want to do your best to space them as evenly as possible. Okay. So we've counted electrons. We've drawn our skeleton. Third step now is to draw our bonds. So we've bonded here, here, and here, right? Because we have to connect our central atom to our outer atom somehow. So each of those bonds contains how many electrons? Do you remember? 2. So how many electrons have we used so far? 6, yeah. We've done 3 bonds, which means we've used 6, which leaves us with 2 electrons left to put on our structure. Okay, is that making sense or not quite so much? Right, we had 8 that we needed to represent. We used 2, 4, 6. Okay? Now we need to complete the octets of these atoms. Okay? Hydrogen and helium are the only 2 atoms that, for right now, don't need octets, right? Because they are in the first energy level and they only have room for 2. So hydrogen is happy on all of these, right? It's got 2 electrons in that bond that it can consider its own. So nitrogen, how many electrons are surrounding nitrogen?
6.
2, 4, 6. So all we're going to do with nitrogen here is add a lone pair. That's it. So now as we count our total electrons, we have 2, 4, 6, and 8. Right, we've used all of them. Nitrogen has a complete octet, 2, 4, 6, 8, and each hydrogen is happy because it has 1 bond. Okay, so this is a completed and happy Lewis structure. Within this bond, one of these electrons is from nitrogen, and one of the electrons is from hydrogen. Okay? And so it contains 2, right? The purple electrons are from each hydrogen. The green electrons are from nitrogen, right? Nitrogen gave 5 to the equation, right? So nitrogen's 5 electrons are 1, 2, 3, 4, 5. Okay, does that kind of make sense a little bit? Okay. Okay. Let's try this one. H2S. Anybody name it?
Sulfuric acid?
No, we're close. No, it's an acid.
Sulfuric acid?
No.
Sulfuric.
Hydrosulfuric acid. Because it comes from sulfide. All right, here we go. So let's count our valence electrons. Hydrogen each gives 1, so we have 2 from the hydrogens plus 6 from sulfur, which is 8 electrons. Which has to be our central atom?
Sulfur.
Sulfur. And so H will go on either side. Okay. Next step is to bond both of these. So we bond here and here. So how many electrons have we used in bonds?
4.
4, which leaves us with 4. Okay, so what do you think an option would be?
2 on top, 2 on
On top of what?
the sulfur.
Okay, so here's a lone pair on sulfur. That leaves us with 2 more. And here's another one, which leaves us with 0. So we needed 8 electrons, 2, 4, 6, 8. So we're good there. Does sulfur have a complete octet?
Yep.
Yes.
2, 4, 6, 8. And is hydrogen's happy?
Yep.
Yes. Okay. Let's try one more here that's a little bit more difficult. PF3. So no hydrogens now. So phosphorus has how many?
5.
5 plus 21, which is 26. Which has to be my central atom here.
Phosphorus.
Okay, why phosphorus?
It's the least electronegative.
Least electronegative, very good. And it's whichever really comes first, okay? Or whichever has the fewest. Okay, both of those are good clues to which should be your central atom. So P, F, F, F. And then I'm going to bond. So in my bonds themselves, how many electrons have I used? I've used 6. So that leaves me with 20 electrons left. So the way, where you go from here is you fill the octets of our outer atoms first. So how many more electrons do I need to make fluorine happy?
6.
6. And they need to be in the form of pairs. So 2, 4, 6. Okay, so that leaves me with 14. I'll do that for the other fluorines as well. So I use 6 more. That leaves me with 8. I'll do that with the last fluorine. And I try to remember remember we have kind of 4 sides to our atoms. So you kind of try to add them on those 4 sides. Not a huge deal, but please at least try to make sure that you can tell that they are paired. Okay, so I've done another 6. That leaves me with 2. Which of my atoms does not have a complete octet? Phosphorus, right? So fluorine is 2, 4, 6, 8. This fluorine has 2, 4, 6, 8. This fluorine is 2, 4, 6, 8. Phosphorus, however, has 2, 4, 6. So what's my solution to make phosphorus happy?
One more lone pair.
A lone pair here. Okay? Yeah, Ethan.
How do we know that phosphorus needs 6?
How do we know that phosphorus needs to have 6?
Yeah.
You mean in terms of its bonds or what?
Never mind.
You got it? Okay. So let's count total electrons. Before you can move on for anything, you have to count total electrons. So total, here I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay, so you don't count the bonds twice, right? When you're counting total, you just count them one time, but they can count for both atoms in terms of the octet rule. Okay, how do we feel about that? Okay, so next class we're going to go over if we can have multiple bonds, and we're going to go over some exceptions to the rules. Okay, but this is a good basic starting point.